If you stood at the Brooklyn Navy Yard in 1943, looking up at an Iowa-class battleship, you were staring at 45,000 tons of hardened steel. Deep in the stern, 4 cast steel struts held propeller shafts carrying 212,000 horsepower. If the bearing bore through even one of those 50-ton struts was misaligned by 0.03 of an inch over 20 feet, the shaft whipped, the bearings burned out at flank speed, and the warship was dead in the water. That bore was not carved with hand tools. It was machined by a machine tool, so colossal its bed had to be anchored to bedrock. That machine was not built in a coastal shipyard or a Pittsburgh mill. It was designed, cast, and hand-scraped on the shore of Lake Winnebago in a Wisconsin factory town named Fond du Lac. The company was Giddings and Lewis. You are watching Rivet and Rebar, where we take apart the companies, machines, and materials that built the physical world. If this is the kind of history you want more of, like this video and subscribe before we go any further. In an era before digital sensors, Fond du Lac built the cast iron leviathans that held split thousandth tolerances across 40 feet of travel. Without them, America could not have machined the turbines for its battle fleets, the blocks for its diesel locomotives, or the hulls for its nuclear submarines. To understand why Giddings and Lewis became the backbone of heavy American industry, you have to go back to 1859, to a marshy basin where the Fond du Lac River empties into Lake Winnebago. Fond du Lac was not an industrial capital. It was a frontier logging outpost. The white pine forests of northern Wisconsin were being felled at a staggering rate, and the river was choked with timber rafts floating towards steam-powered sawmills. In 1859, a mechanic named John Bonnell opened a machine shop in Fond du Lac to keep those mills running. When a water wheel shaft sheared, a boiler blistered, or a circular saw arbor threw a bearing, Bonnell forged replacement pins and poured new Babbitt journals. 7 years later, in 1866, the shop was acquired by the Trowbridge brothers, who constructed Wisconsin's first gray iron foundry and renamed the business the Novelty Iron Works. They were not building fine instruments. They melted scrap metal in a coke-fired cupola, poured molten charge into damp green sand molds, and chipped out crude gear wheels and agricultural castings for local lumbermen and wheat farmers. By 1895, the enterprise was formally incorporated as the Giddings and Lewis Manufacturing Company, named for managers C.M. Giddings and Robert Lewis. For 2 decades, the company thrived by manufacturing heavy woodworking machinery. Massive bands saw mills, reciprocating timber carriages, steam feeds, and log turners. The iron was thick, tolerances were measured with wooden rules and coarse calipers, and business boomed as long as the timber held out. And then, the trees ran out. By the early 20th century, northern Wisconsin had been logged down to stumps and clay. The timber syndicates packed up and moved west to Oregon and Washington. In Fond du Lac, sawmill machinery orders dried up almost overnight. The company was left with a sprawling brick factory, a smoky foundry, and a balance sheet bleeding cash. Giddings and Lewis was staring directly into liquidation. Reorganization came in 1919, when local leather tanner Fred Ruping, who held a major financial stake, stepped in to save the company. He brought in a 38-year-old Bavarian mechanical engineer named Heinrich B. Kraut, known across the shop floor as H.B. Kraut. Kraut had trained in Munich and spent years at Joseph T. Ryerson and Son studying American manufacturing. He was cold, analytical, and unsentimental. When Kraut walked through the Fond du Lac works, smelling damp sand and watching machinists patch obsolete sawmill parts, he saw a dead end. Kraut made an audacious, ruthless decision: liquidate the woodworking line entirely. He announced that Giddings and Lewis would bet its entire future on a single, brutally demanding class of metal cutting equipment: the heavy horizontal boring, drilling, and milling machine. The magnitude of that gamble stemmed directly from the fundamental physics barrier of heavy manufacturing. Throughout the 1920s, American manufacturing was scaling to dimensions that made traditional machine tools utterly useless. Automakers turned crankshafts on engine lathes. Tool rooms ground small bushings. Shipyards bored rings on vertical boring mills, where workpieces clamped to a spinning turntable like a wrecker. On a lathe or vertical mill, the workpiece rotates. Centrifugal balance and rotational symmetry work in your favor. But what happens when the workpiece weighs 40, 60, or 80 tons? Consider a cast steel steam turbine casing, a 12-cylinder marine diesel crankcase, or a locomotive cylinder saddle. These components are massive, asymmetric, and weigh as much as an entire railway freight car. You cannot mount a 60-ton locomotive casting on a spinning faceplate. The rotational inertia would tear the bearings from the headstock and fling 40 tons of iron through the factory wall. The workpiece must remain dead stationary, bolted to the earth. The cutting tool must do all the moving. That sounds simple. It is not. Inside a horizontal boring mill, the cutting tool mounts at the end of an alloy steel spindle extending horizontally from a traveling headstock. To bore deep internal bearing journals through a 20-foot casting, that spindle must reach 4, 5, or 6 feet into open space. And the moment a steel shaft extends horizontally without outboard support, it runs headlong into the unforgiving physics of cantilever beam deflection. A cantilevered spindle sags under its own dead weight. The further it extends, the greater the bending moment. If that rotating spindle deflects downward by even 4/10 of a thousandth of an inch over a 5-foot stroke, the bore is no longer a true cylinder. It becomes a cone or an oval. If the spindle deflects by 1/2 thousandth, the boring bar cuts a taper. If the boring bar cuts a taper, the labyrinth seal leaks. And if the labyrinth seal leaks, the steam turbine loses 20% of its thermodynamic efficiency before the ship ever clears the harbor. The physics barrier went deeper. Cutting heavy nickel steel or chilled iron generates tens of thousands of pounds of opposing cutting force. Those forces push the spindle backward and upward. If the spindle bearings have the slightest microscopic clearance, harmonic vibration sets in. The tool begins to chatter, bouncing against the metal and scalloping the bore surface into washboard ripples. Once chatter begins, high-speed steel cutting teeth shatter like glass. Kraut realized that precision at this scale was not an issue of delicate watchmaker adjustments. It was a problem of structural rigidity, vibration damping, and pure metallurgical mass. He was not selling horsepower to those who made it. He was selling the only geometry that could contain it. Walk into the assembly bays of Plant 1 on Doty Street in Fond du Lac to witness how Giddings and Lewis solved the physics of heavy metal cutting. You are not looking at ordinary machine tools mounted on wooden floorboards. You are standing before monolithic industrial structures designed to carve steel with astronomical rigidity. Giddings and Lewis built two fundamental configurations: table-type mills, where a heavy rotary table supported workpieces weighing up to 30 tons, and colossal floor-type machines, where the workpiece was bolted directly to massive cast-iron ground plates embedded in concrete. On floor-type machines, the workpiece never moves. Beside it, anchored to a separate runway bed that could stretch 40, 50, or 60 feet, sits a monolithic cast-iron column weighing 30 to 50 tons. On the face of that vertical column rides the headstock. Inside that headstock sits the heart of the machine, the horizontal boring spindle. Every single component was an exercise in structural physics. When modern engineers design a machine frame, they often turn to welded structural steel tubing because it is cheap, light, and easy to fabricate. In Fond du Lac, fabricated steel was treated with contempt. Welded structures ring like a bell. Steel has virtually no internal molecular damping. Under the violent shock loads of a multi-tooth milling cutter slamming into armor plate, a welded frame vibrates harmonically, transmitting chatter directly into the cutting tool. The company cast these monolithic frames from gray iron. specifically high-tensile mehanite gray iron, alloyed with nickel and chromium. In this iron, excess carbon precipitates out during solidification as microscopic flakes of graphite disperse throughout a crystalline perlitic matrix. Those millions of graphite flakes act as atomic shock absorbers. Gray iron possesses 3 to 4 times the vibration damping capacity of steel. When cutting forces shock the spindle, the iron absorbs the energy and converts it into imperceptible heat. The frame stays dead. It does not ring. Understand what it took to prepare that iron before machining ever began. When a 50-ton cast iron column freezes in a sand mold, the thin outer walls cool hours before the massive core. That uneven cooling traps violent internal stresses within the crystalline lattice, tens of thousands of pounds of tension and compression waiting to tear the geometry out of true. If you take a fresh column casting directly from the foundry to the planer, it may measure perfectly flat on Monday, but by Friday, as internal stresses relax, the ways will bow by 0.003 of an inch. To relieve that trapped molecular tension, Giddings and Lewis practiced natural thermal seasoning. The raw 50-ton castings were loaded onto flat cars and rolled into an open-air storage yard outside the plant. They sat under the Wisconsin sky for 6 to 12 months. They endured -20-degree winter blizzards off Lake Winnebago, followed by 90-degree summer heat and drenching humidity. This continuous seasonal expansion and contraction gently worked the crystalline lattice, allowing internal stresses to relieve themselves naturally. The iron surrendered its violence to the weather before a single cutting tool touched its skin. Once the castings were seasoned, they entered the machining bays for planing and grinding. But even the finest German or American planers could only machine the guide ways to within 1/1000th of an inch. A machine tool that weighs 40 tons cannot ride on a planed surface. Freshly planed, waste surfaces are covered in microscopic tool marks and directional scallops. If you place a 40-ton column on raw planed iron, the high ridges make contact on less than 5% of the surface area. The localized pressure squeezes the lubricating oil out like water from a sponge. The moment the feed drive engages, the metal galls, tears, and seizes in a phenomenon machinists call stick slip. No machine could provide that solution. It required an artisan, the hand scraper. Along the runway beds in Fond du Lac stood veteran toolmakers holding heavy, hardened steel scraping bars tipped with tungsten carbide. Leaning their chests and shoulders against the scraper handles, they used their entire body weight to peel away microscopic curls of cast iron. To guide their cuts, they used the ritual of Prussian blue. A scraper took a master straight edge, a massive bar of aged cast iron or granite, hand-lapped to absolute optical flatness, and smeared its surface with a film of Prussian blue paste made from ferric ferrocyanide pigment ground in light mineral oil. He lowered the heavy straight edge onto the machine ways, rubbed it back and forth, and lifted it away. Wherever iron touched iron, the blue transferred to the high spots. The low spots remained clean. The scraper raised his chisel and sliced off the blue-stained high points, taking off 0.2 of a thousandth of an inch with every thrust. He did not scrape the surface dead smooth like glass. If you scrape away dead flat, two matching iron surfaces will ring together like gauge blocks, creating a vacuum locking them solid. Instead, the craftsman scraped an intricate, deliberate pattern, 20 to 25 discrete bearing contact points per square inch, surrounded by shallow microscopic valleys engineered to retain oil. Under motion, that lubricant formed a hydrodynamic wedge. A 40-ton column that could crush a truck was supported on an unbroken film of oil 0.2 of a thousandth thick, so perfectly balanced that a machinist could glide it along the bed with the turn of a single cast iron hand wheel. That same obsession governed the spindle. Heavy boring requires a dual mechanical personality, massive low-speed torque for large facing cutters, and smooth high-speed rotation for deep precision boring. Giddings and Lewis engineered a concentric two-spindle architecture. A massive outer sleeve, running on heavy preloaded Timken tapered roller bearings, carried large milling cutters. Concentric inside that sleeve sat a high-speed inner spindle forged from nitraloy alloy steel. This inner spindle was not merely heat-treated. It was placed inside sealed electric retort furnaces and baked in an atmosphere of anhydrous ammonia gas at nearly 1,000 degrees Fahrenheit for 90 hours. Nitrogen atoms penetrated the steel, forming needle-like iron nitrides that produced a glass-hard outer case measuring Rockwell C70. It was diamond-hard, impervious to scoring from razor-sharp iron chips, and ground to concentricities measured in 100,000ths of an inch. To keep the headstock from deflecting the vertical column, a massive iron counterweight hung inside the column bore, suspended by multi-strand roller chains over ground sheaves. The counterweight matched the headstock pound for pound. The vertical elevating screw never carried the dead weight of the iron. It carried only the cutting vector. Precision is not manufactured. It is transferred. A machine tool cannot produce a cylinder straighter or a face flatter than its own guide ways. Every split thousandth bore machined into an American battleship turbine or submarine hull was born directly from the calloused palms, scraping chisels, and blue paste of the men in Fond du Lac. In the late 1930s, as war clouds gathered across Europe and the Pacific, the United States Navy embarked on the most colossal shipbuilding program in human history, the Two-Ocean Navy. Congress authorized billions of dollars to construct dozens of fleet aircraft carriers, hundreds of destroyers, and the largest battleships ever conceived in the Western Hemisphere, the 45,000-ton Iowa class. Washington soon discovered a terrifying bottleneck. You can appropriate billions of dollars from the Treasury and draft millions of young men into uniform, but you cannot lay down an aircraft carrier or a battleship without machine tools. And at the absolute pinnacle of that industrial pyramid sat the heavy horizontal boring, drilling, and milling machine. Every major naval shipyard in the country, the Brooklyn Navy Yard, the Philadelphia Naval Shipyard, Newport News, Fore River, and Norfolk, was backed up waiting for machines. A capital warship is not merely a steel hull. It is a floating fortress of high-pressure thermodynamic machinery, heavy ballistic armor, and precision artillery. And almost every critical component required heavy machining on a scale that only Fond du Lac could deliver. By 1940, well before Pearl Harbor, the United States War Department arrived in Fond du Lac with an urgent contract. The federal government financed the construction of a dedicated 7-acre emergency plant facility, Plant 2, built directly adjacent to Giddings and Lewis's existing shops on Doty Street. It became one of the most advanced heavy machine tool complexes in the world. The Fond du Lac works shifted to continuous 24-hour production, running 3 8-hour shifts, 7 days a week. The foundry poured hundreds of tons of mehanite iron every week, and the night sky over Lake Winnebago glowed with the orange exhaust of the melting cupolas. Understand what was riding on those machines. Consider the triple 16-inch gun turrets of an Iowa-class battleship. Each turret was an armored citadel weighing over 1,700 tons, heavier than an entire Fletcher-class destroyer. That massive structure rotated on a 30-foot roller path and had to elevate 3 66-foot gun barrels in perfect unison. The cast steel trunnion bearing blocks, armor plate mountings, and traversing rings had to be machined on Giddings and Lewis floor-type boring mills. If the trunnion bores were out of alignment by even 0.002 of an inch, the heavy guns would bind during recoil, jamming the battleship's primary battery in the middle of a fleet engagement. Down in the machinery spaces sat cross-compound steam turbines manufactured by General Electric in Schenectady and Westinghouse in Leicester, Pennsylvania. These turbines turned superheated steam at 850 degrees into 212,000 shaft horsepower. The massive split turbine casings had to be machined so true that no soft gasket material was used to seal the joint. Gaskets would blow out under 600 pounds of steam pressure. Instead, the upper and lower halves of the 50-ton steel casings were planed and bored on Giddings and Lewis machines to bear metal-to-metal tolerances, sealed only with a thin brush of boiled linseed oil. If the machine tool chattered or cut a taper, the joint leaked and the warship lost propulsion. To drive that horsepower into the sea, long line-boring setups running through 4 ship bulkheads and 40 feet of hull had to be machined in a single, dead-straight optical alignment for the propeller shaft stern tubes and outboard struts. Barely 60 miles north of Fond du Lac, Manitowoc Shipbuilding constructed 28 fleet submarines on Lake Michigan. The massive opposed piston diesel engine blocks that powered those submarines through the Pacific were bored on Giddings and Lewis machines, as were the heavy cylinder blocks for the locomotives that kept America's rail network moving. On the shop floor in Fond du Lac, hundreds of women joined veteran toolmakers under the Navy E-pennant, checking bore tolerances with inside micrometer sets, operating giant radial drills, and breathing the hot mist of mineral cutting oil. But the machine tool builder occupies an unsettling, detached position in the architecture of war. A boring mill does not distinguish between a commercial locomotive and a warship. In the 1930s, before pre-war export embargoes were clamped shut, American machine tools had been exported globally, machining armaments for nations that would soon become battlefield enemies. The artisan scraping iron on Doty Street never saw the concussive muzzle blast of a 16-inch gun at Leyte Gulf or the burning hull of a torpedoed vessel. He only knew the smell of sulfur oil, the heavy thrum of the planer, and the cold geometry of the way. The steel was never the moral variable. The customer was. When World War II ended, Giddings and Lewis did not retreat into peacetime complacency. The onset of the Cold War created engineering challenges that pushed metal cutting past the limits of human sensory perception. The United States was entering the nuclear and jet ages, and both demanded machining on a scale never before attempted. In Groton, Connecticut, at General Dynamics Electric Boat, and down in Virginia at Newport News Shipbuilding, the United States Navy began building the nuclear submarine fleet under the relentless, abrasive direction of Admiral Hyman Rickover. In 1954, the world's first nuclear-powered vessel, USS Nautilus, slid into the Thames River. Its pressure hull was formed from heavy HY-80 alloy steel, engineered to withstand the crushing hydrostatic pressure of the ocean abyss. Boring through HY-80 steel, an alloy with 80,000 pounds per square inch of yield strength, demanded immense tool rigidity. If the spindle vibrated, the tool work-hardened the tough nickel-chrome steel into glass, ruining expensive cutters and creating microscopic fatigue risks. The massive hull penetrations, reactor foundation support pads, and precision torpedo tube clusters were bored and faced on colossal Giddings and Lewis floor-type machines. In nuclear propulsion, a microleak in a reactor coolant loop or a distorted hull seam is fatal. The iron from Fond du Lac held the line. Simultaneously, the United States Air Force faced an aerodynamic crisis. High-speed jet bombers like the Boeing B-52 Stratofortress required wings, machined as single, monolithic ribbed panels from solid aluminum alloy slabs, eliminating thousands of riveted joints. Hand-guided milling could not trace the complex mathematical contours. In 1955, Giddings and Lewis, backed by Air Force funding and partnering with MIT researchers who formed Concord Controls, unveiled Numericord. It was one of the first commercial numerical control systems in the world, using multi-channel magnetic tape to direct multi-axis spar and skin milling machines without human intervention. Fond du Lac had helped usher in the digital manufacturing age. And then, the accountants arrived. By the late 1960s and 1970s, the culture of American industrial manufacturing was undergoing a profound and damaging mutation. The engineer executives who had spent their lives listening to spindle bearings and reading Prussian blue were replaced by corporate managers trained in finance. To an accountant in an executive suite, an 80-year tradition of hand-scraping ways, seasoning raw iron in the snow, and maintaining apprentice programs was not an irreplaceable core competence. It was merely a bloated cost center with a high payroll to be pruned for quarterly margin. The friction between shop floor craftsmanship and corporate austerity erupted into open hostility in the autumn of 1975. In October 1975, the International Association of Machinists Local 1402 walked out on strike at Giddings and Lewis in Fond du Lac over wages, seniority rights, and restrictive work rules. It became one of the longest and most bitter labor disputes in the history of Wisconsin manufacturing, dragging on for 14 agonizing months. Management took a radical, precedent-setting step. They hired 323 permanent replacement workers to cross the picket lines. In a close-knit Wisconsin community where second- and third-generation toolmakers lived on the same streets as shop foremen, the town was torn in two. Lifelong neighbors stopped speaking. Picketers stood outside the Doty Street gates in sub-zero January gales, watching replacements walk past to run the machines their fathers had built. Veteran scrapers watched men who had never touched a straight-edge try to read blue paste on 30-foot ways. Union members finally voted to end the strike in November 1976, but returning workers were not restored to their former positions. They were placed on a preferential recall list, fighting a protracted legal battle that dragged all the way through the National Labor Relations Board to the Seventh Circuit Court of Appeals. The unwritten social contract of the industrial Midwest was broken. What followed was a dizzying carousel of corporate ownership. In 1982, Canadian conglomerate AMCA International acquired Giddings and Lewis for $310 million, restructuring it as a corporate automation segment. MCA spun it off in 1989. In 1991, Giddings and Lewis absorbed its battered Wisconsin rival Cross and Trecker, bringing Milwaukee's legendary Kearney and Trecker into the fold. 6 years later, in 1997, German conglomerate Thyssen acquired the company, followed later by private equity ownership under MAG through every leveraged buyout, conglomerate acquisition, and corporate restructuring. Financial engineers extracted cash and cut overhead. They treated an 80-year reservoir of mechanical competence like a financial commodity. But you cannot financialize the physical laws of cast iron. Step into a heavy manufacturing plant today, a power generation facility in Schenectady, a locomotive maintenance bay in Altoona, or a naval shipyard in Norfolk or Puget Sound. Alongside rows of sleek, sheet metal enclosed 5-axis machining centers with touchscreens and polycarbonate safety glass, look over at the heavy bay. Bolted onto a reinforced concrete pad that drops 20 feet to bedrock sits a colossal, dark green machine tool. Cast into its massive column face is a cast iron nameplate. Giddings and Lewis Machine Tool Company, Fond du Lac, Wisconsin, USA. The original controls are long gone. The hydraulic tracer attachments, the early magnetic tape readers, and the analog vacuum tube electronics were ripped out decades ago. Modern machine rebuilders have retrofitted the machine with digital readouts, high-torque brushless servo motors, ground precision ball screws, and contemporary computer numerical control systems. But the foundation of the machine, the 50 tons of mehanite gray iron, the hand-scraped prismatic boxways, and the massive nitrided spindle, remains untouched. If you wipe away the film of heavy whey oil along the bottom of the column, you can still see the faint, rhythmic crosshatch flaking marks carved into the iron by a scraper's chisel in 1952. Those microscopic oil pockets have held hydraulic pressure through 3 generations of round-the-clock production. Ask the shop superintendent why the company spent $500,000 rebuilding a machine built 70 years ago instead of buying a brand new imported machining center from Europe or Asia. And he will give you a simple answer. You cannot buy that iron anymore. Modern machine tool builders design their frames using finite element computer modeling, optimizing structures for minimal shipping weight and lower material costs. They build columns out of welded structural steel tubing or cast them thin. But fabricated steel plate rings under heavy interrupted cuts, and modern castings are rarely allowed to sit in an open-air yard for a full year of seasonal thermal cycling. They lack the deadening mass and internal molecular damping of 80-year-old Wisconsin mehanite iron. That 50-ton column on Doty Street has spent more than half a century under compressive preload. Its internal casting stresses relaxed completely during the Eisenhower administration. Its molecular lattice is settled, inert, and dead to harmonic resonance. When a 6-inch carbide face mill bites into a 50-ton block of forged steel, the machine does not flinch. It absorbs the shockwave into its bedrock foundation and leaves a surface finish as smooth as ground glass. Today, the Giddings and Lewis name survives as part of the Industrial Engineering Group 5s, still maintaining precision manufacturing operations in Fond du Lac. But the great era of monolithic American iron, when a small Wisconsin city on Lake Winnebago stood as the master arbiter of heavy precision for the entire Western world, belongs to the past. Every politician who authorized the two-ocean navy is dust. The conglomerate executives who bought, stripped, and traded the corporate trademarks are gone. The paper balance sheets have dissolved into corporate archives. Yet the iron remains. The machinists who ran those machines every day were never told the full story behind the nameplate. Now you know it. The archive of stories like this one keeps growing. So subscribe to Rivet and Rebar, and we'll see you in the next one.